Yeah. So yeah, I've been working on millimeter wave and sub-millimeter wave VLBI, mainly working with the Event Horizon Telescope. And I'll talk about one of the main things that I've been focusing on the last couple of years, which is calibration of high frequency VLBI observations. So this work was done in collaboration with quite a few people, like Lindy Blackburn, Tom Bessie, and Paul Tita, whose names you'll see popping up once in a while in this talk. So it's quite a good group working on calibration that I'm part of now. And yeah. So I'll start with a basic introduction to radio interferometry. So people might be aware of single dish observations. So on the left, you see the power pattern of a single dish antenna on the top. And when you start adding more elements and start operating it as an interferometer, you start seeing this fringe pattern. And the size of this fringe pattern is determined by the distance between the antennas. And as you increase the distance between the antennas and the interferometer, then you start seeing these fringes becoming sharper and sharper, and you get higher and higher resolutions. So the idea with an interferometer is to measure the mutual coherence function of the electric field at two different locations. And that's what you see over there. And that's a simple two-dimensional Fourier transform expression, which dictates how the sky brightness is recorded when observed using multiple radio telescopes as interferometers. So very long baseline interferometry is quite similar to how we do connected element interferometry. So connected element interferometry is it consists of arrays that everyone knows of, like Cat7 or MeerKAT. Very long baseline interferometry follows the same principle, but it uses dishes that are separated thousands of kilometers apart. In principle, they can be located all over the world. And this complicates the very fact of like the way you do calibration, the way you do data analysis. So here are some examples of VLBI networks that are currently operational. There is the European VLBI network, which has a lot of stations in Europe, some in East Asia, and there's one at Hartrau in South Africa. There's also the very long baseline array, which consists of multiple radio telescopes in all of US and also in outside of continental US in Hawaii. And there's also the global 3mm VLBI array, which conducts observations. So this is already quite high frequency at 86 gigahertz. And it also has some stations in Europe, and also consists of stations in VLBA and also ALMA. So I work with the Event Horizon Telescope. So the EHT it famously produced the black hole, the resolved black hole images of M87 and Sgr A. And on the right, you see the polarized M87 image that was published in 2019, and later the polarized images were published in 2021. And Sgr A was published in 2022, and polarization information was published last year. And you see remarkable consistency between the ring structures in these two different black holes, although they are 3 orders of magnitude different in size. And in 2018, we also published, last year we published the 2018 data of M87, and this is remarkably consistent with the 2017 observations. So that gives us confidence that VLBI technique is working at millimeter waves. So this happens at 230 gigahertz. And 2018, we also had additional stations, and we got really nice images. And we've been trying to improve our calibration and imaging algorithms in anticipation of more stations joining the EHT. So a quick overview of the VLBI measurement process. It's quite similar to connected element interferometry, but there are additional factors to take care of here. The curvature and movement of the Earth itself comes into play when you start doing VLBI, when your stations are separated thousands of kilometers apart. And one of the most important differences between something like the EHT and MeerKAT is that the clocks that are used at different stations are dependent. All the MeerKAT stations are connected to each other, and they share the same clock. So when it's a certain time at one station, it's the same time at a different station or a different telescope. That's not the case. That's not necessarily the case with VLBI. So you have to first try to make sure that these clocks are aligned with each other before you even try to form the mutual coherence function. And there's also absorption and emission and additional path delays and potentially noise that reduces your signal to noise due to the troposphere or ionosphere, depending on the frequency at which you're observing. And the atmosphere over the different stations could be vastly different because they're located in different parts of the world. And also the stations that participate in a VLBI observation tend to be heterogeneous. The designs may be different. The mounts may be different. The dish sizes may be different. The frequency setup of the different stations and different observatories could be different. And this is generally not the case when you do connector element interferometry. Polarization feeds, there could be leakage between the two orthogonal polarization feeds that are used in any experiment. There could be differences in path delays between the polarization feeds and the recorder, and these could be different. The paths are independent. And this could differ from station to station. That's another thing that you need to take care of in VLBI. And that could also be complex in sense of consisting of an amplitude and phase, complex bandpass effects, and also receiver gains that are varying in frequency and time. And we also need, so all of these factors can affect the phases and amplitudes, mainly the phases. A lot of the calibration process that I described pertain to the phases that you measure. And you also need to do a step of amplitude calibration. People who are familiar with radio data calibration with CASA might see some similarities between the process that I described in this. Although certain steps may be slightly different, conceptually they're all the same. So for amplitude calibration, you always need additional metadata from the different stations. And this is also easier if the same observatory is operating all the telescopes, like MEERKAT. So when you have stations that are separated widely around the world, then you rely on people working at the independent observatories to provide you the metadata in the right form. And there are many things that could go wrong here that you'll know. You'll kind of see that the data are weird when you do your calibration. So calibration itself is the process of correcting for all of these propagation path effects to recover meaningful astrophysical signals. The first step in doing interferometry is to perform correlation. And the EHT uses a software correlator called DIFX. EHT consists of 4 frequency bands, each about 2 gigahertz wide, around the main observing frequency of 230 gigahertz. And so 2 bands are correlated in Bonn, 2 bands are correlated at the MIT-HOPS Observatory in Massachusetts. And there are some, they do correlate some common data to ensure that they're doing the same thing, the right thing. And the correlators use something called a correlator model or an EHT model, which accounts for the geometric delay as a function of time. The geometric delay is the delay between the arrival times of the same electromagnetic wave at different stations that participate in the experiment. And this could be affected by a lot of things. Some things that could affect this are the very geometry of the array and the direction in which the source is. Like for some stations, the source may be overhead. For some stations, the source may be near the horizon, and that could affect the geometric delay. And there's also the atmospheric contributions to the delay. And there's also clock offsets, and there are frequency standards that can drift over time that you can actually see in the data. The bottom block diagram is just to show that, show how the resolution is reduced right from the Nyquist sampling at the correlator to the correlator output and the calibrated output. So EHT has 4 bands, each of which has 32 channels of 58 megahertz each. It's roughly 2 gigahertz per band. The calibration pipeline that I've been working on is the EHT. It's called the EHT-HOPS calibration pipeline. HOPS is the Haystack Observatory Post-Processing System. It was originally driven by the requirements of geodesy and high-frequency astronomical VLBI. And in the 2000s, when computers got really fast, software correlation became possible for experiments like these. And software correlators re-emerged about like 10 to 15 years ago. And this all enabled the use of HOPS for EHT calibration. So we've been working on this pipeline. So it was originally published in 2019 to extend the basic HOPS functionality using an additional Python library called the EHT analysis toolkit, or the EAT library, to perform certain additional calibration steps that were not needed for geodesy and were not originally present in the HOPS program. And so I've been working on developing this further, and we have refactored the pipeline, and we have added a bunch of new features to this pipeline, with the aim of calibrating data from any past or future EHT campaign, and not just EHT data, but also other similar VLBI arrays at high frequencies, so that we can quickly provide reference calibrated data products so that people can compare with their own calibration or their own imaging analysis. So there are a couple of challenges here. The EHT is an evolving array. It's heterogeneous array. It's a heterogeneous array of single dish arrays, single dish antennas, and phased arrays. So earlier, ALMA used to be the main phased array that was participating in the EHT. Now we also have NOEMA, and we also have SMA. We're not observing only at 230 gigahertz. We are also observing at 345 gigahertz, which is about 870 micrometers. And these observations, the very first test observations were successful. And in the last couple of years, these have become routine, and they are expected to be part of regular EHT campaigns going forward. So just a quick introduction to the radio interferometer measurement equation. Apologies if you already know this. So this provides the theoretical foundation for radio interferometry. When you do a full polarization radio observation using two orthogonal polarization feeds, there is a matrix called the coherency matrix that you can form using the electric fields at the two different antennas. So you have EX, so X and Y are the two polarization states, and they are a combination of, so EX, EY is an electric vector from one station, EX star, EXY star is an electric vector from the other station, and you can form this 2x2 matrix that encapsulates all the information. So you might recognize the Stokes IQ UV components, and this is the simple mathematical relation between how you do interferometry and the four Stokes components. So from this, you can extract all the polarimetric information about the source that you're observing. So you can make a series of 2x2 matrices called Jones matrices, which kind of encapsulate all the propagation path effects that I've described so far. So the main difference between calibrating the observations of a connector element interferometer and a VLBI experiment is a process called fringe fitting. And this is a necessary step in VLBI calibration. So the takeaway from this is that you don't just calibrate for a complex number when you're trying to estimate your instrumental effects. It's not just an amplitude and phase, but your phase itself consists of multiple terms. There is a phase offset term. The phase can vary with frequency, and the variation of phase with frequency can vary with time. So all of this needs to be corrected for when you do VLBI calibration. So I'll just go through a set of sequence of steps that are necessary to do this process. And you may notice some similarities with CASA calibration here too. So at the very beginning, what we do with HOPS is we kind of set search windows. So for phases, like what range of phases do you want to search for, and how much variation with frequency or how much variation with time you expect in these phases, called the delays and delay rates. And so you set windows for all this using certain keywords in HOPS. And you also set some flags, like if you already know some data are bad, usually the correlation centers provide you with some information of which data are bad or where some stations just dropped off. So you can remove all the data and set some search windows and start your calibration process. So the first step that we do is to calibrate the phases over the bandpass. So our software can derive this variation of phase with frequency with one term or one delay per frequency channel. So we have 32 channels over 2 gigahertz, and you derive the phase slopes, and that's what you see at the bottom. You derive the phase slopes for each frequency channel for the different stations, and these are all baselines reference to ALMA. A is ALMA here, there. And then you correct for these phase slopes. So this corrects the phase variation over frequency or over your bandpass. with the result that like on the top, you see a sample reduction of GMBA data. So the red curves there are phases. So on the top, you have how the phases look before phase bandpass. So over the bandpass of GMBA, you see the phases kind of doing a curve like this. And then after phase bandpass calibration, they're all kind of aligned around 0. So this kind of takes away the frequency dependent effect. And then this is one of the things that's most important to do at 230 gigahertz or 1.3 millimeter, where there are nonlinear random phase fluctuations on the time scales of seconds that are introduced by the atmosphere, which is mainly the troposphere. The ionosphere really doesn't play a part here. And so you can see on the right here, before we correct for it. So because these phase variations happen at the time scales of seconds, you can't really integrate your data for more than a few seconds. But if you want to build up a high signal to noise ratio, you should be able to average your data over minutes or even over entire scans, which we often do in the EHT. So you can see here, again, the red curves. You can ignore the blue curves, they are the amplitudes. So you can see the red curves, like before you correct for the tropospheric effects, there's a lot of turbulence in the phases and they're just all over the place. And so you kind of use a phase structure function to optimize these tuning parameters. And then you kind of correct for these every few seconds so that the phases line up. So after ad hoc phasing, the same phases all line up and like flat, like around the 0 point. And now you know your data are looking good and you can average over longer time scale. And then, so these are a couple of other important steps that we need to do. So all the solutions that I've been describing above correspond to each baseline. So if you have like 10 stations that participate in your VLBI experiment, all these solutions are baseline based. But you actually want to derive solutions that are station based. So that's what's called the globalization step or like global fringe solutions. Before you can do that, you just want to make sure that the delays, which are the phase variations over frequency, and the delay rates, which are phase variation, which are the variation of delay over time, can be or aligned between the two polarization feeds. And so this alignment can happen if you have a very strong station. And luckily with the EHT, we have ALMA often participating in the station, at least for part of the night. So the ALMA there's the relative delays between the two orthogonal polarization feeds in ALMA are calibrated carefully, and you can expect them to be 0. So we use that property of ALMA to reference all the other phases to ALMA phases to make sure all the other delays or delay rates to ALMA delays, and try to align the left and right delays and delay rates for the different stations. So on the right, you see a sample plot of like after this alignment for like all the different stations. You can see, so these are for like 2 different sources, the blue and red curves. You can see them like a nice histogram around 0. So the delays and delay rates have been aligned between the 2 polarization feeds. And so after this, you can stationize the gains, and now you have a parameter, a delay, a phase, and a delay rate parameter per station, which allows you to reach down to signals at a much lower SNR. So we've been talking about phase calibration. The whole process of fringe fitting is a kind of generalized phase self-calibration. We haven't done any amplitude calibration yet. So finally, we do something called amplitude calibration using a priori information provided by the stations. So the first thing that we do here is HOPS has its own file formats, so called fringe files. So we have our own scripts to convert this to UV-FITS files in a way that the imaging software can analyze this data. And so we collect metadata from the stations, such as the ANTAP files, which have the system temperature, which records different temperatures, like the instrumental temperatures, the receiver temperature, and also the atmospheric temperature over the different stations. So we need this information to get an idea of how much the amplitudes can be attenuated when you're doing calibration. And the VEX files or schedule files, so they tell you at what times the observations were conducted, and the mount types. The station mount types are also necessary to kind of correct for the fact that certain stations may rotate with respect to the sky, and you need to correct for this factor before you can average your data. So all of this information goes into computing what's called the SCFD, which are used to scale up the visibility amplitudes. So here is an example of how they look after you scale up the amplitudes. So I just want to draw your attention to the bottom part here. So that is how so this is an M87 plot. And when you plot it against the baseline length, you start seeing a pattern like this. And this pattern is the Fourier transform of a ring. So even before imaging, you have an idea that, oh, maybe you're going to see some kind of ring-like structure from just by looking at these complex numbers. So in addition to this whole process, we made some more improvements to our software. The EHT bands are about like 58 megahertz per channel and over a 2 gigahertz bandwidth. And they're said to overlap with the ALMA channels because the ALMA channels are of a different size. But then in 2021, NOEMA became part of the EHT array, which had yet another different size for each of their individual frequency channels. So now we have the kind of frequency bands that we expect for the EHT. We want the stations to have, but ALMA has something else and NOEMA has something else too. And what this does is, because of this mismatch and because we have these phase variations over frequency, you can get phase jumps in the middle of the frequency channels, especially where NOEMA is concerned. So, and you can see, like, for example, the first row here shows the frequency setup of NOEMA, and the second row is the frequency setup of ALMA, and the third is the frequency setup of SMA. And you can see that, and the SMA frequency, you can consider that as kind of like the zoom bands that you want. And there's only a partial overlap with the NOEMA stations. So we have implemented some additional procedures to kind of flag parts of the spectrum so that these mid-channel phase jumps don't occur for NOEMA, so that we can retain most of the NOEMA data. And another important is probably the most important feature that we have introduced for our calibration is to do with polarization. Just to give a quick overview, so the polarization is usually measured using two orthogonal feeds. It's usually linear or secular polarization. So the two feeds, like the one that you see here, can either measure linear or secular polarization, as shown here. And traditionally, VLBI arrays have used either linear or secular polarized feeds to measure polarization. So this is the equation that you saw earlier. So the four Stokes components just translate easily to the four complex visibilities that you measure. But EHT is a special case. It observes in a mixed polarization mode, where ALMA uses linear polarization feeds and other sites use secular feeds. So all baselines to ALMA record visibilities in what's called a mixed pole basis, where the electric field from ALMA is in a linear basis and the electric field from the outstations are in a secular basis. So the relationship between the four Stokes components and the four visibility components are more complicated. So like this. So it's not a simple expression like just an addition of like I plus Q and I minus Q. And if you just take these two components, you can easily get your Stokes I full unpolarized amplitude. It's not that simple with the EHT normally. But this transformation is also governed by a single matrix, a single static matrix that you can introduce in the Jones chain when you're calibrating. And that will come in handy when, in the next slides. So when there are instrumental effects, and there always are instrumental effects, the station gains and the additional polarization, complication introduced by polarization must be known in advance before visibilities in mixed pole basis can be calibrated. So the standard practice is to wait for ALMA to finish their quality assurance, the QA2 process, and obtain gain tables from them, and then use a software called PolConvert, written by Ivan Marti-Vidal, to convert ALMA data to circular basis. So now when you form the complex visibilities, all the data are in circular basis and the easier Jones equations can be applied. But there's an issue with this. The ALMA QA2 process is lengthy and it's a significant source of delay. Often it takes more than a year before we can even start calibrating the data that were taken a year ago. And if there are issues that are not identified in the QA2 process, they can cause problems for PolConvert. These errors can kind of like propagate down to the data where you start seeing weird things in the data. there is an alternative where we can try to calibrate the mixed pole data. These are available much earlier from the correlation centers. So the single static matrix here can be introduced in your calibration process to convert the data to circular polarization basis on the fly. So you can get your ALMA data in linear polarization and other data in circular polarization, and you can just, with the addition of this matrix in your equations, you can easily calibrate mixed pole data. And here is how we tested our mixed pole data calibration. So we have a software called Comrade, developed by Paul Tida, which is a Bayesian imaging framework. It also simultaneously solves for some instrumental models while imaging. And so on the left, you see what we had with the EHT 2017 data. So if you go back to the EHT 2017 papers, you'll see images like this. And these are from the pole converted data after ALMA data had been like completely converted to circular polarization. And on the right, you see the image that we obtained using this calibration pipeline and Comrade to image the M87 data. And you can see that qualitatively, you can see that the ring structures are remarkably consistent with each other. And there is a small southwest extension, which when you solve for in mixed pole basis, kind of disappears. So this is due to instrumental effects. And these are the kind of effects that you can uncover when you operate on the data without having additional software packages trying to change the polarization basis in between. So just a brief overview of the pipeline architecture. So the flowchart can look complicated, but all this shows is that all different data files that are in like different folders and subfolders in the data archive are linked to the working area, which is under the pipeline directory. And the metadata are also extracted from the appropriate places, and also some flag information provided by the correlation centers. And all the steps are done in order. So these are all the different steps that I described earlier, separated into different scripts. So they can, for features that are not available in the HOPS software, the EAT library, the Python library is called, and the additional steps are performed. So at the end of this process, you get your calibrated data in UEFITS format. So this pipeline is now public, and the metadata and data diagnostics are separated from the main repository. So anyone can download and use their own metadata information and own notebooks to provide diagnostic summaries. And we also provide some Jupyter notebooks for providing data diagnostics and data summaries, like the ones that you see there, like for example, the delays or the phase variations in frequency that I was talking about. So you can kind of, so you'll get these outputs when the pipeline functioning, the pipeline finishes the reduction, and you can immediately see where are the outliers, and either flag the outliers or see if something went wrong in the calibration process. And I've also been developing a more dynamic data diagnostic interface using Julia, and this will also hopefully soon become part of the pipeline itself, so that people can just start the pipeline and then just start dynamically playing around with the calibrated data. And so HOPS 4 is coming out. So far, we've been using HOPS 3, and so we have a lot of expectations for HOPS 4. A couple of things that I want to draw your attention to is that so we only talked about like phase bandpass corrections, but HOPS 4 will support both phase and amplitude bandpass corrections at sub-channel resolution, not just at 58 megahertz, but even the resolution before correlation. And also there will be native support for mixed circular and linear polarization basis. So a lot of workarounds that we have implemented for mixed pole data analysis can be just moved to HOPS 4. And also a global multi-band calibration and frequency phase transfer capabilities will be introduced in HOPS 4, where the frequency phase transfer is the process of solving for phases at a lower frequency, where you can average data for longer timescales and then porting those solutions to higher frequencies so that the same solutions apply at higher frequencies and the longer term averages are enabled. So we're also doing this in anticipation of the next generation EHT. So we are looking at developing flexible calibration models to describe both source variability and propagation path effects. and including the behavior of the instrument on the different stations at the ngEHT frequencies. We expect to make simultaneous 86 and 230 gigahertz and 345 gigahertz observations. The fractional bandwidths are expected to be wide, and the UV coverage will be dense, and the dynamic range will be improved. And unlike the EHT campaigns, which last for about 2 weeks, the ngEHT campaigns are expected to last for 3 months on a 3-month time scale. So you can actually propose for monitoring campaigns with the ngEHT. And there's a 12 orders of magnitude in data reduction as you go from the raw signals to correlated data to calibrated data to finally an image or a movie. And there are also potential ngBLA, ngEHT, and GMBA observations. And these are especially useful for SAAO star, because the SAAO star jet is like too weak. We can't really detect anything. But with simulations, you can show that with ngBLA, GMBA, and ngEHT at 86 gigahertz, you can maybe start seeing some extended structure. For all this, the methods that I've described above and methods that are in the pipeline to be developed will be useful. So this is just a summary slide. So our pipeline is public and it's ready to be used for any millimeter and submillimeter VLBI calibration. And HOPS is very fast. Like even like large data sets are calibrated in a day or 2 at the most. And so we can still set this up to provide reference data sets for people doing their own calibration and analysis. It has a composable architecture. So currently we're using HOPS 3 and EHT executables, but the calibration steps are kind of plug and play. You can use your own software with some small changes to the scripts that drive the process. And support for additional features for like native support for mixed pole data or complex bandpass corrections will come in HOPS 4, which will be integrated into the pipeline soon. And yeah, frequency phase transfer, which is a very important technique for high frequency, especially sub-millimeter wave calibration, will be part of HOPS 4 and this pipeline soon. And it will use a modern binary data format, which is way easier to access from Python, which is not the case currently with HOPS 3. So we have to do a lot of things just to access and organize the data properly. So over the next few months and a year or so, you can expect this pipeline to get even faster. And if you have any VLBI observations or data that you want to calibrate, yeah, feel free to contact us and we'll be very happy to help you and accommodate your needs. So, thank you.
Common data in the past wait sometimes a year for that. So then what was the time scale of the overall sort of data reduction you need to do to get to from the raw data to get to, let's say, getting some polarization images like that? And how is sort of this and getting sort of on the fly capability take that?
Yeah. So so for example, the 2017 observations were published in 2019 and the polarized images were published in 2021. So that's like 4 years. And the 2018 data were published only last year. I mean, there were also like 4 big delays, stuff like that. But I think as the data get more and more, you need people who can actually like sit down and look at the data, like and start looking at like doing spot checks on the data. And that process itself can take long. And subsequent, like since 2021, we've had NOEMA as part of EHT, and more stations keep. So it's almost like every year you're observing with a different telescope. That's been the case with EHT. And the idea here is to, and you normally wait for maybe like 6 months or 9 months or 1 year, maybe even longer than 1 year for this ALMA QA2 process. You can, at least with certain software, like for example, with the HOPS calibration pipeline and Comrade imaging software, you can arrive at images way faster. Like you can cut down a year or a year and a half. But of course, not all software packages are capable of doing a mixed pole analysis. So there's a lot of room for improvement to develop these capabilities in other imaging packages and calibration packages too. And if you have maybe a couple of different calibration software or different imaging software that can handle mixed pole data, then you can before waiting for the Alma QA2 data, you can even start, getting images that you can kind of maybe circulate within your team or circulate within the collaboration members to get an idea of how good your data are and how much changes that you can expect when the Alma QA2 data arrive. So right now, you can't even do the process of this calibration, amplitude calibration, without the Alma QA2 data. But now we already have potentially images and also a set of tests that you can immediately perform as soon as QA2 data become available. So I would think that would easily cut down like a year or so from like raw data collection to publication.
I have a question, but it's not about this. I don't know whether it's allowed like to be said or not. But like, what is the data set that the EHT team is working on at the moment?
So we have published, I think, almost all of 2017 data, and 2018 M87 data have been published. But there are still like other AGN sources, and also we haven't published anything from 2021, 2022, 2023. So there are different teams working on different data sets.
So are there all the observations are only from M87 and Sgr A?
No, there are other AGN sources. So which are sometimes used as calibrators for M87 or Sgr A observation. Sometimes there are separate proposals for observing those AGN sources. So with like different PRs. So there are different teams working on it.
Okay, I don't see any more questions, so let's thank you.
One more question.
Oh, yeah.
It's a wider question for EHT. Like you mentioned ngEHT, ngEHT, all these things to me. What is the status on new stations being added to EHT? And if there are new stations, like I know there's a millimeter telescope sort of talking about in Namibia, but are there kind of big constraints now where you're like, look, if you want to be a part of EHT, please sort of have this particular setup, or you're like, look, we'll just welcome anyone that comes in if you have the same frequency range.
I think there are some stations which already exist, and probably with less effort can become part of EHT. But there are some ngEHT stations which are like entirely new, which are and the EHT or ngEHT collaboration will like help like whatever site that has been chosen to like put up and like maintain, or maybe even like bring new receivers at higher frequencies for those stations, even if they're not equipped currently. So that kind of mainly depends on the weather characteristics and the accessibility of the site. So there are like ngEHT, like over the next few years, ngEHT is expected to add maybe almost up to 10 sites compared to what we had a few years ago. And yeah, ngVLBI, I don't work ngVLBI. Yeah.
No? Okay, then let's thank Iniyan again. Thank you.